Welcome to the AP Chem channel, where we help you learn chemistry the easy way by showing you how to solve problems. Today's video is our second one for the 2019 AP Chemistry test. So this one is on the solutions to question number 2 in the free response question section of the 2019 AP Chem test. We have a video for question number 1, so you might want to watch that. And also, every year after the AP test, they publish the questions for the FRQ section. So you can just go to the AP website and download a copy of the test. And if you haven't done that yet, you should probably do that before you watch the video so that you know what the questions are. But if you have a copy of the questions already, then let's check out the solutions. Question 2 in the free response section of the 2019 AP Chem test is about these halogens. So part A asks you to look at these 4 different diatomic molecules, Br2, Cl2, F2, and I2, and it asks you which one of these has the longest bond length. These are diatomic molecules that are made up of basically the group 7 elements. So in the periodic table, group 7 has elements F and then Cl, Br, and then I. And so in the periodic table, they are arranged in this way, and these are called the halogens. And so because of that, you can see that out of these 4 diatomic molecules, I2 should have the largest bond distance. And that is simply because I2 being the one that is farthest down on the periodic table should have the largest atomic radius, because you put more and more electrons as you go down a column in the periodic table onto these atoms. So as a result of that, I being the one on the bottom is expected to have the largest atomic radii. And because of that, it also would have the largest bond length. B, let me write down some of the data that's given in the problem before I start talking about this. So the question gives you the half reaction potential for 3 different half reactions, Br2 plus 2 electrons going to 2 Br minus, and here the table gives you basically the half reaction reduction potentials in terms of volts. This is 1.07. And then the second one in the table is Cl2 plus 2 electrons going to 2Cl minus, and that's 1.36. Finally, it gives you I2 plus 2E going to 2I minus, and that is 0.53. The question says you have basically 3 different compounds at your disposal, and these are NABR in an aqueous solution, Cl2 gas, as well as I2 solid. And what you want to do is to use any of these 2 to make the product, which is Br2. So the question is, how do you prepare Br2 from these compounds. So if you look at the half reaction potentials, you can clearly see that if you want to make Br2, Br2 is on the left side of the first half reaction. So you need to put that on the product side. So what you want to do is to take the first one and flip it around. So let me just write that. So I'm going to have now 2Br minus on the left side and Br2 and 2 electrons on the right side. Of course, if I reverse the direction of the reaction, I change the sign of the half reaction potential. So this one now becomes 1.07 volts. And I need to then combine that with another half reaction so that I can produce Br2. And so the one that you would need to combine with is the one that provides you a large enough reduction potential to overcome that minus 1.07 volts for making Br2. And that's obviously taking the chlorine, because this one is not sufficient. So take the second half reaction as it is, and it becomes 2Cl minus. The half reaction voltage for that is 1.36 volts. So now you see that if I add up these two reactions, then I will get a total reaction which does produce Br2 on the right side. The electrons cancel, and so you are basically putting together Cl2 and 2Br minus, and that would produce Br2 plus 2Cl. And you see that the total voltage is just the sum over these two, and that is equal to positive 0.29 volts. So that is a spontaneous reaction, and in this case you are in fact producing the Br2 starting with Cl2, which you have, and also starting with Br minus, which comes from this sodium bromide aqueous solution. Before I go to the next part, let me just emphasize one point. When you add two half reactions together, you will get a voltage, but the voltage that you get do not need to be multiplied by the stoichiometric coefficient that you need to put in to multiply each half reaction. It turns out for this case, in this particular reaction, both of these half reactions, you just take 1x of each in order to build up the entire balanced equation. But even if you were to use different pieces of each half reaction to combine to form the total reaction, when you compute the overall potential of the cell, you would still not include the stoichiometric ratios of how many half reaction of the first one plus how many half reaction of the second one. To produce the overall cell potential, you really just take the two half potentials and just add them together. So part C, it tells you that there are basically two different boiling points for Br2, which is 332K, compared to BRCl, which is 278K. So these are boiling points. So I'll just write them as BP. So clearly, based on the boiling point, you see that because the boiling temperature of Br2 is higher than BRCl, then you expect that there is larger intermolecular interactions between Br2. So we have I should say intermolecular interactions in Br2. So the question is asking you to explain why. Well, so both of these are, according to the reaction, they are liquid, so they will, at a high enough temperature, vaporize into gas phase molecules. So to vaporize into the gas phase, you have to break the intermolecular interaction between the individual molecules. So for example, in this case, you have these molecules which are basically between different molecules in the liquid phase. When that evaporates into the gas, then these molecules are no longer close to each other, and so whichever intermolecular force that you had between them in the liquid state, these are lost when that liquid evaporates into a vapor. So a higher boiling point means that there is a larger amount of intermolecular force in the liquid state for Br2 compared to BrCl. And so the question is, why is that the case? Well, so if you look at that, you can understand that Br2 has no dipole moments. So this is a non-polar molecule, whereas BrCl, because Br and Cl have different electronegativity, is certainly polar. So you know that polar molecules can have what is called a dipole-dipole interaction between them, whereas nonpolar molecules will have none of that because there is no dipole in a nonpolar molecule. But in all molecules, as long as they have electrons, they will have what is called a London dispersion force. So both of these molecules do have dispersion interactions. The reason is because any molecule that has electrons can have these London dispersion interactions between them. However, the molecules have larger London dispersion forces are generally the ones that are larger, or the ones that have a larger number of electrons. So you see, as we have said, because Br is lower than Cl, Br has more electrons than Cl. As a result of that, Br is a bigger atom, and at the same time, it also has more electrons, and so its dispersion forces is stronger. So if you have a molecule that is made up of two Br atoms versus BrCl, which is made up of one Br and one Cl, then you can see that the dispersion interactions between Br2 and other Br2 molecules is bigger. So this dispersion forces is stronger. So even though the Br2 molecules are nonpolar and do not have dipole-dipole interactions between them, it turns out that their size leads to a stronger dispersion force in Br2 compared to BrCl. So as a result of that, that is the reason why this the boiling point of Br2 is higher than BrCl. Part D, the problem says there is a reaction where 2 BrCl can make Br2 and Cl2. So let me just write down that reaction first. So the reaction is 2 BrCl making Br2 and Cl2, and the problem tells you the delta H for that reaction is equal to positive 1.6 kilojoules per mole. And so the problem tells you in the reaction you mix together some BrCl in a flask. So let me write down the data that we are given. So we have 0.100 mole of BrCl in a flask which has the volume equals to 2.00 liter, and the temperature is 298 K. So the problem tells you that you are putting that in this container and you're waiting for the system to reach equilibrium. And so the first part, which is part D, is asking you to calculate the initial pressure inside the container before the system moves to equilibrium. So this is fairly simple just by using the ideal gas law. The reason is because you really only have one ingredient inside that box. So let's write down everything we know. We know PV is equal to nRT. We know the number of moles in this case is 0.100. I'm just going to skip the units. We know the gas constant, which is 0.08206 liter atmosphere per mole per degree K. And finally, we have the value for T, which we know is 298. And on the left side, we know one of the values. We know the volume is 2.00 liter. So with all of that, we can easily calculate what the pressure is. So the pressure will turn out to be just nRT over V. And if you plug all of those numbers in, the pressure will come out in units of atmospheres. And so let me just very quickly write down everything. This is divided by 2.00. At the end, the pressure is 1.22 atmosphere. Now, before we calculate the equilibrium constant, part E of this question asks you to write down the equilibrium expression for this reaction. So the reaction we're talking about is this one. So the equilibrium expression K is expressed in terms of the partial pressures of the reactants and products. So this is partial pressure of Br2, which is the first product, multiplied by the partial pressure of Cl2, second product, divided by the partial pressure of BrCl. But remember, since there is a coefficient of 2 in front, this is raised to the power 2. So this is the equilibrium constant expression for that reaction. And part F asks us to take the information that's given in the problem and calculate the value of this equilibrium constant. So the piece of data that we are given for this problem is that at equilibrium, uh, 42% of the BrCl has decomposed. So we notice that from part D, the initial partial pressure of BrCl is 1.22. So if 42% of that has decomposed, then the final pressure at equilibrium of BrCl must be the original partial pressure multiply by what is left. And what is left is obviously 1 minus 0.42. And so if you calculate what that is, you see that the equilibrium partial pressure for BRCl is 0.71 atmosphere. So we have that number right there. So we still need the partial pressure of Br2 and the partial pressure of Cl2. But of course, those are given by the stoichiometry of the problem, because according to the balanced equation, every time 2 BrCl decomposes, it makes 1 Br2 and 1 Cl2. So in this case, you see the amount of BrCl that has decomposed is 42%. And because every 2 BrCl makes 1 Br2 and 1 Cl2, then the amount of Br2 is equal to the amount of Cl2 that is created by the decomposition of BrCl, and that is also equal to just 42% of 1.22 atmosphere. But since the stoichiometry is 2 to 1 to 1, each one of them is just one part, so you divide that by 2. And if you do that, you will find that the partial pressure of both Br2 and Cl2 are 0.26 atmosphere. And so finally, if you take those numbers and put them into the equilibrium expression, then you can calculate the value for the equilibrium constant. So this is 0.26, 0.26, and in the bottom we have 0.71, but do not forget about this 2. So after you put everything in, you see that K turns out to be 0.13. Finally, part G is asking you to calculate the bond energy of BrCl. But before I start the problem, again, let me write down some of the data that is given. The problem gives you the bond energy of these 3 bonds, a Br-Br, a Cl-Cl, and a BrCl. The bond energy, of course, is expressed in terms of kilojoules per mole. And for Br-Br is 193. For Cl-Cl is 243. And we want to calculate the BrCl bond energy. If you remember earlier, we have the delta H for this reaction right there. So let me point that out again. I'm going to write that down in the with part G so that you can see what's going on. But in this case, what we want to do is to notice that the delta H of this reaction is known. It's 1.6 kilojoules per mole. So let me just take that equation and write it down again. So we have 2 BrCl going to Br2 plus Cl2, and delta H for that is plus 1.6 kilojoules per mole. Now that we have the data in this table, then we know the bond energy of Br2 and the bond energy for Cl2. Then we can use this equation to calculate the delta H of the reaction by adding up basically all the energies of the reactants. So this is basically sum over all the energies of Br2 and Cl2. So let me just write energies. And subtracted from that, the energies of 2BrCl. Okay. So normally this would have been written as delta H's, right? So this is delta H of the products, and this is delta H of the reactants. So using the bond energies that are given, we can figure out what each of these are. So first of all, for Br2, the bond energy is 193. So the delta H of forming a Br2, delta H0 of Br2, is equal to 193, except is actually negative 193. The reason is these bond energies are listed for the energy that is needed to break a Br-Br bond. So if you take that and make two separated Br, breaking the bond between them, the energy that is needed to be put in, so there's this energy that needs to be put into the reaction, is equal to 193. So what that means is that the molecule is more stable than the two atoms separated. So this bond energy is actually stabilizing the molecule. So delta H of Br2 is actually 193, but with a negative sign. So let me just emphasize that right here. So notice this negative sign. And similarly, delta H of Cl2 is the negative of the Cl-Cl bond energy. So it's negative 243. Let me use the same color to be consistent. Negative 243. And now we have the delta H of the reaction on the left side. So delta H is equal to 1.6 and positive. So what we can then do is just set up an equation to calculate delta H of all the reactants, which are the 2BrCl. So let me write the equation up here. 1.6 positive. I'm just going to leave out the units because they're all kcals per moles. So the 2 with negative values are these. And then subtracted from that is the delta H of the 2BrCl. And so you can just put that into your calculator. And you see that the delta H for 2BrCl will come out to be minus 437.6. So to just round, we can probably just say 438. Now, but that's for 2Br2. So for each one, it's 1/2 of that. But we remember that the delta H is actually the negative of the bond energy. So what we will do to get this value is to take 1/2 of 439, but take the positive sign. So at the end, what we will get for that is just 219, and the units are kilojoules per mole. And so that's the bond energy for BrCl. Okay, so that's the end of this problem. And in the next video, we will go to question number 3.